Hello. Hello. I'm Patrick, and this is Joey, and we're going to talk to you today about generating worlds from the top down and bottom up with machine learning. We work at Player Unknown Productions, headquartered in Amsterdam, and the studio was founded with a kind of an ambitious vision to make really large worlds, Earth-size with thousands of players, to encourage emergent gameplay. We both work in the machine learning team. And with this giant goal, we saw machine learning as a tool we could use to achieve these larger scales that we're looking for. And that's the rest of our great team. Along the way to this vision, which we call Artemis, these are the two projects that we have, which are both attacking the problem of scale at different ends. The first, going back, is attacking it from the smaller scale. And Preface, Tech Demo, is attacking it from the top down. And to start off, I'll pass it off to Joey.
Hi, can you hear me? Yes. Okay, cool. So it's worth talking about what is generative machine learning. Obviously, everybody's talking about generative machine learning, but what is it? Unfortunately, we can't do like a whole course on it just in this half an hour. But it's enough to say that machine learning takes a data set, which is a data set is just pairs of inputs and outputs normally, and it learns to imitate it. It learns to take this input and transform it into an output. So that input can be something like, say you could imagine a machine learning model that could take an image of a dog, and then the output would be a guess at what that dog's bark sounded like. But it could also be something like the input could be a random noise field, and the output could be something you wanted to get like maybe it was an image or something like this. And in that way, we can feed in random noise and get sort of new, different stuff out of it. And you must have heard over the past couple of years, but over the past 10 years in particular, machine learning has brought new, exciting opportunities. So for one, we have this concept of these multimodal, strange inputs and outputs. So the example of the sound and images, but it's really anything that can be represented as numbers on a computer, which everyone in this room knows is quite a lot of stuff. So we can do images, sounds, etc. in principle, but we can also fold in other stuff such as player data, things like this. All of this stuff can end up being an input or an output to a machine learning model. And also, it turns out that machine learning has become a lot more capable in recent years. So you'll see, stuff like LLMs and things like this, which are creating really amazing things. And so we've really made some steps forward. So the actual process of creating a machine learning model is sort of two-stage. The first is this sort of learning stage. So this is the learning in machine learning, where we take this data set of inputs and outputs. And this is typically, as anyone who's worked with machine learning, depending on the complexity of your task, is tons and tons of data. So this is an extremely strenuous part of getting this data. And it's worth mentioning at this point at Player Unknown Productions, we don't use any copyrighted data, or just everything that you'll see in this talk is from data that, free data or data we own or stuff like this. But yeah, so this learning step is something that will take a lot of time. So for the landscapes that we talk about today, we have some very powerful, expensive GPUs that will take weeks to train. But what we want to do is we want to make sure that we can run these GPUs on a player's laptop, so just a normal gaming PC. So we have to make sure that the model we output from it will run in GPU seconds. So a sort of a standard GPU will take seconds or milliseconds essentially. And we find that ML models are capable. So I asked ChatGPT to make me a bowl of slop, and it gave me this incredible image of a bowl of oatmeal. Like, if you'd shown me this 10 years ago and told me an ML model had created this, I'd say that's impossible. Like, the level of detail, the sort of composition, the fact that it interpreted me saying slop and turned it into oatmeal is amazing. And it's hard to deny that is obviously very impressive. But the thing is, I asked it 3 other times to generate me a bowl of slop, and it created me 4 completely different images that were all effectively the same. So what we know about machine learning models through working with them is that they're not creative and that they don't want to explore the space. They don't want to say, what could slop be? What bowls could I put this slop into? It's just, I'll make the easiest imitation of slop and give it to the person who's just asked me for it. And on top of that, if we don't explicitly code them in, there's no levers to these machine learning models. They're black boxes. We can't just go into a machine learning model and say, okay, now I want a spoon in the oatmeal bowl. We have to go back and we have to add spoons into the training data and hope when we want the spoon comes out. We have to or we have to add in these explicit levers. So sort of dealing with this 10,000 bowls of slop problem led us to this concept that we call guided generation. So our principle with this is that we know people are creative. So there's a lot of creative people in this room. There's a lot of creative people in our company. That they're level designers, tech artists, or even players. But we know it takes a lot of time to create something. But the machine learning model is scalable. It can exist on my computer. It can run in a few GPU seconds and create something entirely new. So what we want to do is create these, design these ML models from the start to work directly with creative people. So, and when I say input here, I don't mean that the people are giving input, like giving oversight input to how we should train a machine learning model, but literally passing input to a machine learning model, and then combining that with sort of seeded noise, we can generate interesting outputs. So the way to think about this is that the input will be sort of a sketch or an idea of something that somebody wants in a game or some sort of content, but sort of a non-detailed version. And then the machine learning model can take that sort of sketch and some random noise and generate something that is unique every time but fits that sketch. That's the sort of concept we're aiming for. So to make that a little bit more concrete, Remco and Michael talked yesterday about our game Prologue, go way back. And yeah, so it's a survival game. It's coming out in summer. Please play it. It's a lot of fun. But importantly, every single time you boot up the game, there's an entirely new 64-kilometer squared chunk of land that has been generated on your computer in a few seconds, hopefully, depending on how good your GPU is. And what we thought is because this is sort of an open world sort of exploration game, a lot of us here have played Breath of the Wild, Elden Ring. We know elevation is a humongously important part of like showing off the map to users. So they'll be able to see, okay, I want to go, like they get to the edge of a cliff and they say, oh, I want to go and check that bit out over there. Or they get sort of, it's then a barrier from them to go to one place to another. And also, you know, ever since we started playing games, sort of rivers and oceans have been a good border to say, okay, you're not allowed to go here, or it's going to be harder to get over this way. So we thought, okay, let's get our sort of level designers, anyone can draw a river and sort of give us a rough mountain area, and this will be sort of the sketch. This is the idea of the map. We then combine that with the machine learning model and some random noise, and it will take this sketch and create a sort of like high resolution landscape with this sketch, where the sort of details, the bit that takes time, will have been created by the machine learning model, but the sketch, the rough idea of the map, will follow this sort of sketch. Yeah, so when we do this, and we have put this in the game, here we go. We find that even with one river schematic here, so this is one example, passing this through the model 5 different times, we get maps that all encode this gameplay, sort of the fact of the river going this way across the map, but the actual individual maps will feel different every time because the sort of small scale, medium scale structure of the map is completely different. And yeah, so we haven't yet had any complaints from any players saying, oh, you know, I've gotten the same river twice, etc. Like people actually find that the maps are different and fun. On top of that, because machine learning normally has a really long iteration time, but because we've directly encoded these levers, we can control them really quickly if we want to iterate on something and find something new. So we found there was quite a heartbreaking moment in our first playtest where we were watching a playtester play, and they came up to the edge of the river, and they were like, "This is not a river. This is a lake." They saw it was so wide. They turned left, and they were trying to get around the lake, but you could tell they were just about to walk off the map because it was a river and not a lake. So we found that we could, instead of having to go all the way back to the drawing board, remake the data, et cetera, because we had this as a lever, we could iterate, make the river smaller, and and it became a sort of gameplay feature of, you know, players need to find the sort of smaller parts of the river to cross, because crossing the river is a pain. But it's not perfect, and guided generation is still sort of a machine learning model and still is a black box. So we have a couple of problems, one being a systematic one, well, some being systematic ones. For example, our current model in Prolog will, every now and then, about 5 to 6% of the times that we generate, will generate these barren mountain maps, we call them, which essentially you come out of your cabin and it looks like you're on the moon because it's just everything's a mountain, there's no vegetation anywhere, and these are obviously very bad. We haven't been able to get rid of this on the machine learning side, so what we do is we do a sort of post-processing step where we check the map, see if it looks like it's mountain everywhere, and if so, we'll simply throw out the generation and start all over again. But because this machine learning model is so quick to run, it'll only add a couple of seconds onto the startup time of the game for any, for sort of, 1 in 20 startups of the game. But then we have these sort of long tail, I think it was called earlier, these long tail problems that we never even predicted to happen. So once we started giving the game out to playtesters and we were having thousands of maps generated, someone screenshotted it and put it to the Discord saying, there's a massive square on my map. And my initial reaction was, that's a UI bug, you know? Somebody's just accidentally put a square icon on the map. There's like, no way. This is anything to do with the ML because we don't have any squares in the training data. We would try to avoid that. Because the way this looked on the map, it would be sort of like a massive obelisk in the middle of the map, which is, we don't have. But then sure enough, because we have the ML seed and because this is all reproducible, we looked at this height map and there it was, the obelisk. Which is obviously a problem. And these are the kind of things that we could add a post check as well to check that there's no big squares, but then there'll be a big oval or a big hexagon that turns up and then we'd be screwed. So this is the stuff that the game team has to deal with and has to make sure that no matter how bad the generations are, that it's still a playable map, and they do that very well. But then there's upsides as well. So Remco talked yesterday about how we're using real-world data that's been augmented by Houdini to sort of encode gameplay features. And I don't know if Remco would agree with me, but the ML model seems to output maps that have those features, and it looks good, for one. But because it's actually done with real-world data, it has real drainage networks in it. So we were finding that once we had a big main river that was going through a Prolog map, that there were these sub-rivers that the ML model was just trying to include. It knew, it was like, oh, a river this big should have a sub-river, have tributaries going into it. So these are things that we never asked it to do, but because it had encoded the sort of concept of what a landscape should be and what the real world should look like, it's great. It's something that came out sort of by accident, I'd say. And then on top of that, like these erosion patterns are also really important for gameplay. So we have the sort of higher sort of cliff lands and then the lower lands, and the erosion patterns are the way that people go from the lower lands to the upper lands, which is again part of Remco's training data. But these all come out naturally, and the drainage networks sort of people can follow the drainage networks and know that they're going to go up or go down and stuff like this. And so it really feels like you're walking through the real world, which is really exciting. But obviously, so this is Prolog, and this is how we're sort of like trying to deal with the small scale encoding interesting gameplay features and stuff like this. Our goal long term is to go to sort of Artemis, these planet-sized worlds. So Patty's going to talk about that.
Yeah, so to talk about the top-down, now we know that we can generate small-scale, realistic terrains. How can we scale this up to planet size? Here's a little video. Preface is a tech demo of our in-house engine called Melba, which has machine learning integrated, it's a long loading screen, sorry, integrated deeply into the engine. And when you go closer to the surface of the planet, at each scale, it up-preses the terrain using machine learning models, so that when you go to the surface, that data was generated for the first time when you get there. Yeah, so it's a technical demo. It's really just a testing ground for our in-house engine, which has this first goal to prove out the scalability of Earth size. To do this, there's 2 steps. The first thing is we generate a full map of the world offline, including all the data layers. All of these layers we're trying to replicate real GIS data. And when the player goes onto the planet into some small region, we run what we call multi-layer upscaling, which is a machine learning model which runs runtime in the engine, each frame. And you can kind of see little flickers there, which is the upscaling happening at each step, which is doubling the resolution. It's kind of like Enhance from Blade Runner. But actually, in here, it's kind of giving you the impression that it's finding information that was there in the image. But in reality, what we are doing is it's generating stuff. It's going from 1 kilometer per pixel to 1 meter per pixel of resolution in the terrain. So it is imagined in that sense. We use a combination of quad tree in the rendering system, plus this upscaling model to go all the way down to the surface. So each time we split the tiles and go close to the surface and increase the resolution, it is increasing the resolution by 2 times. This is just following super resolution image generation literature in machine learning, standing on the shoulders of giants. And importantly, it's happening to all of our data layers which make up our base data structure, which is height map and texture and other information. At the moment, we generate these maps offline, only for a pragmatic reason, so that we can explore the space of how we can integrate this kind of guiding into it. And the engine itself uses multiple layers to actually render out height map, satellite texture, and biome labels. Here's an example. The machine learning model generates a height map, which is then applied for the terrain mesh. And you can see the quad tree overlaid over there. And then also it generates a satellite texture, which is then used as like a long distance view, albedo texture. And then we procedurally generate biome labels and tree density from the height map to allow us to place assets. The first of the models that we use in this process is a height map generator. And to train this, we got real GIS data, elevation data, and we blurred it. So we now had an input, which was a low resolution smooth curve, and then the output was the high resolution real mountain. And what happens is the machine learning model learns to kind of fill in the details, as Joey mentioned before. And what this means is we can procedurally generate smooth, low resolution things with different types of noise, and the machine learning model then will kind of fill in the details and make it more realistic. Importantly, these are at 1 kilometer per pixel resolution. We're making this giant initial data. And then we also need to generate texture for the satellite view. Initially, we just paired satellite imagery with elevation data and gave it the elevation data and told it to generate a texture. But the problem was that it would generate deserts or forests arbitrarily, 50-50, because the elevation data doesn't have enough information to tell you what the color should be, because there's other climate influences which are really driving that view. So then we included tree density and biome labels, GS data, which allows the model to actually, it can know that there should be trees there, because otherwise there is no information for it to achieve that. While those models work, there are some challenges with scaling. The first 2 images you see up the top are like, we trained a model to generate satellite imagery, but with no control. It was just random. So each time you see those pictures, they're just random generations. Some of them might look realistic, but they're not useful for us because they don't really link to anything. We can't use them in the engine. And it kind of comes back to this point of like, if you're looking in the distance and you see a green mountain or a snow-capped mountain, when you go there, the assets, there should be trees. If it's green, there should be trees. And then kind of on the bottom here is another point, which is we need to blend across tiles. The generations these are single generations beside each other, and we need to blend between them so we can go to the full scale. And to do that, we have this kind of unidirectional pipeline. We start off with that input contour to generate the height map. And then after that, we can do some procedural stuff to create some like temperature maps and wetness and things to then create some biome labels, also procedurally. And then again, we can create some more rules to create some tree density masks. And then finally, all these three inputs, as we said before, lead in to generate the satellite texture. And if you look at it all together, we can kind of then step back and just modify our initial input contour. We can do it with noise here. We could also sculpt it. Well, actually, it's not noise. This is a sine curve. But we could sculpt it manually, or we could use any kind of procedural thing we'd like. And then the other problem of scale. Oh, that's obviously the vertical consistency between the layers of data that we want to render. But we need to go across the whole planet, which at this resolution in the game, it ends up being thousands of tiles to generate. But we can take the same pipeline, so it's a single generation. Our machine learning models have a fixed output resolution because we train them. So they can only output 512. But we can use the same pipeline and do a sliding window across a larger input contour. And as you can see, each one is related. There are some mistakes there, but with some naive blending, we can get much more consistency. And so this is just the satellite texture, but we do the same for the same kind of general process across the other layers of data. I mentioned naively blending because there is machine learning literature to do this inside the neural network, but this one is much simpler for now. An interesting point is that this continuity of our control signal that we gave the model, the smooth contour, it allows the model to more easily get it right. And then finally, what's next? So far, we've just been thinking in 2D for this. If you boot up Preface, you'll see it's a globe, but actually under the hood, it is a cube, which is projected onto a sphere. And so initially, in our first deployment, we just did our best to generate a whole planet as we could. But as you can see there, obviously, these were generated 2D. We weren't thinking about projection. We weren't thinking about the globe at all. So finally, there's some results from last week. We've been experimenting using the same pipeline, which is hopefully one of the advantages of machine learning, in that we can now sample, if we sample the noise from a 3D space, then project it onto a sphere, and then project it back onto the cube, our noise is then distorted in the same way in which it would be if you had mapped a sphere onto a cube. So now our control signal is also distorted in the same way. And when we pass this to the same pipeline as we did before, the outputs from the machine learning model also contain the same distortion. And this is likely due to the fact that our training data actually included imagery across the world that was distorted in different ways. You know, up near the poles, it's going to be more stretched, and near the equator, it is undistorted. Which this is kind of like the ML oddities. We didn't necessarily expect that it would work, but there was more value in the model than we hadn't retrained it. We're just using the same model. And that's it. Thanks very much.
Okay. I may be getting ahead a little bit, but down the road, are you guys experimenting with people, as in populating it with people down the road? Like an NPC generator?
Yeah. I don't think we could talk about whether we are or not, but yeah.
That's the right question.
Very good question, GP. I have another one. You just said So in the example you gave, the zoom in example you gave, you went down to the small plants on the ground. What happens if in whatever game mechanics you throw down one tree, when you zoom out and zoom in again, is that tree on the ground still? And how do you handle this?
That's a really good question. That's actually one of the technical challenges to face. We haven't worked that out yet, basically.
Thanks.
Hey, have you at any point tried like a 4-channel network so that you would train and infer the height at the same time as the texture?
Yeah, I want to try that. That makes sense. It's kind of like the foundational models, yeah. I think it's probably likely that generating everything at once will be much faster and more consistency.
Okay,
100%.
I think this is really cool. Once I graduate, I also kind of want to work on projects like this. My question is, when you're using machine learning algorithms, they are looking mostly at terrain and color and shape, but not necessarily at like biome. So, like for example, if you look at the terrain features inside the Amazon, they're very different from terrain features in the Sahara. How are you guys accounting for that? How do you prevent things from just looking like it's a noise with some texture slapped onto it?
I guess that's a tricky one. I mean, is your question that that actually the height map that you might generate is different in different locations? There's another information that's missing possibly for generate height map. That's a good question. We don't really control that yet. I think there's other possibilities we might use, such as like text labels. We might use because. For example, biome labels. We can get GIS data for biome labels, and that might be good information. But it's the right way to think that yes, more information will get the model to be able to apply particular styles. We haven't tried that yet, but there's also like maybe a step change with maybe text or other more how would you say, like text is very wishy-washy input. And maybe biomes are very specific. Does that make sense? Yeah.
Yeah, I'm here. Thanks for the talk. Pretty ambitious project, I must admit. And because of that, I have this kind of question related to actual model architecture you mentioned several times about. So because of kind of enormous things to be aware of, what's your like input data and what's the architecture of this model? Are you use your own like creation, like convolution by output layer, et cetera, or you like use some kind of transfer learning for output layers? Like, what's your approach on that? Thanks.
So yeah, it's a great question, and we'd want to go more into detail on it, but yeah, it's a bit sort of inside baseball. But yeah, so what we're using for Prolog is a control net. So it's a latent diffusion model, which is trained completely from scratch. So we're not using any pre-trained model parameters or anything, but we train on Remco's data this diffusion model, which sort of step by step creates a landscape. But then we take that and try to condition it by the rivers and mountains of the training data, essentially. So which then gives us this output model at the end. For the upres, is that that was a yeah, it's a GAN, is it? We're using a generative. Well, we tried a bunch of different things with the upscaler.
Okay. Thank you very much. We need to set up the audio nicely for the next talk, so I think that we can start with it.
Thank you.